carved on the roofs of temples. Each player starts with an equal number of stones, and the object of the game is to move them around the board, capturing your opponent's counters on the way. As the players sat around waiting to make their next move, perhaps one of them realised that sometimes the balls fill the circular holes of the Mancala board in a rather nice way. He might have gone on to experiment with trying to make larger circles. Perhaps he noticed that 64 stones, the square of 8, can be used to make a circle with diameter 9 stones. By rearranging the stones, the circle has been approximated by a square. And because the area of a circle is pi times the radius squared, the Egyptian calculation gives us the first accurate value for pi. The area of the circle is 64. Divide this by the radius squared, in this case 4.5 squared, and you get a value for pi. So 64 divided by 4.5 squared is 3.16, just a little under 2/100ths away from its true value. But the really brilliant thing is the Egyptians are using these smaller shapes to capture the larger shape. But there's one imposing and majestic symbol of Egyptian mathematics we haven't attempted to unravel yet: the pyramid. I've seen so many pictures that I couldn't believe I'd be impressed by them. But meeting them face to face, you understand why they're called one of the 7 wonders of the ancient world. They're simply breathtaking. And how much more impressive they must have been in their day, when the sides were as smooth as glass, reflecting the desert sun. To me, it looks like there might be mirror pyramids hiding underneath the desert, which will complete these shapes to make perfectly symmetrical octahedrons. Sometimes, in the shimmer of the desert heat, you can almost see these shapes. It's the hint of symmetry hidden inside these shapes that makes them so impressive for a mathematician. The pyramids are just a little short to create these perfect shapes. But some have suggested that another important mathematical concept might be hidden inside the proportions of the Great Pyramid: the golden ratio. 2 lengths are in the golden ratio if the relationship of the longest to the shortest is the same as the sum of the 2 to the longest side. Such a ratio has been associated with the perfect proportions one finds all over the natural world, as well as in the work of artists, architects and designers for millennia. Whether the architects of the pyramids were conscious of this important mathematical idea, or were instinctively drawn to it because of its satisfying aesthetic properties, we'll never know. For me, the most impressive thing about the pyramids is the mathematical brilliance that went into making them, including the first inkling of one of the great theorems of the ancient world, Pythagoras' theorem. In order to get perfect right-angled corners on their buildings and pyramids, the Egyptians would have used a rope with knots tied in it. At some point, the Egyptians realised that if they took a triangle with sides marked with 3 knots, 4 knots and 5 knots, it guaranteed them a perfect right angle. This is because 3 squared plus 4 squared is equal to 5 squared, so we've got a perfect Pythagorean triangle. In fact, any triangle whose sides satisfy this relationship will give me a 90-degree angle. But I'm pretty sure that the Egyptians hadn't got this sweeping generalization of their 3-4-5 triangle.
We would not expect to find a general proof because this is not the style of Egyptian mathematics. Every problem was solved using concrete numbers, and then if a verification would be carried out at the end, it would use the result and these concrete given numbers. There's no general proof within the Egyptian mathematical texts.
It would be some 2,000 years before the Greeks and Pythagoras would prove that all right-angled triangles shared certain properties. This wasn't the only mathematical idea that the Egyptians would anticipate. In a 4,000-year-old document called the Moscow Papyrus, we find a formula for the volume of a pyramid with its peak sliced off, which shows the first hint of calculus at work.
For a culture like Egypt that is famous for its pyramids, you would expect problems like this to have been a regular feature within their mathematical texts. The calculation of the volume of a truncated pyramid is one of the most advanced bits, according to our modern standards of mathematics, that we have from ancient Egypt.
The architects and engineers would certainly have wanted such a formula to calculate the amount of materials required to build it. But it's a mark of the sophistication of Egyptian mathematics that they were able to produce such a beautiful method. To understand how they derived their formula, start with a pyramid built such that the highest point sits directly over one corner. 3 of these can be put together to make a rectangular box, so the volume of the skewed pyramid is 1/3 the volume of the box. That is, the height times the length times the width divided by 3. Now comes an argument which shows the very first hints of the calculus at work, thousands of years before Gottfried Leibniz and Isaac Newton would come up with the theory. Suppose you could cut the pyramid into slices. You could then slide the layers across to make the more symmetrical pyramid you see in Giza. However, the volume of the pyramid has not changed, despite the rearrangement of the layers. So the same formula works. The Egyptians were amazing innovators, and their ability to generate new mathematics was staggering. For me, they revealed the power of geometry and numbers, and made the first moves towards some of the exciting mathematical discoveries to come. But there was another civilization that had mathematics to rival that of Egypt, and we know much more about their achievements. This is Damascus, over 5,000 years old and still vibrant and bustling today. It used to be the most important point on the trade routes linking old Mesopotamia with Egypt. The Babylonians controlled much of modern-day Iraq, Iran and Syria from 1800 BC. In order to expand and run their empire, they became masters of managing and manipulating numbers.
We have law codes, for instance, that tell us about the way society is ordered. Now, the people we know most about are the scribes, the professionally literate and numerate people who kept the records for the wealthy families and for the temples and palaces.
Scribe schools existed from around 2500 BC. Aspiring scribes were sent there as children and learned how to read, write and work with numbers. Scribe records were kept on clay tablets, which allowed the Babylonians to manage and advance their empire. However, many of the tablets we have today aren't official documents, but children's exercises. It's these unlikely relics that give us a rare insight into how the Babylonians approached mathematics.
So this is a geometrical textbook from about the 18th century BC, and I hope you can see that there are lots of pictures on it, and underneath each picture is a text that sets a problem about the picture. So, for instance, this one here says, I drew a square 60 units long, and inside it I drew 4 circles. What are their areas? So this little tablet here was written 1,000 years at least later than the tablet here, but it has a very interesting relationship to it. It also has 4 circles on in a square, roughly drawn, but this isn't a textbook, it's a school exercise, so that the adult scribe who's teaching the student is being given this as an example of completed homework or something like that.
Like the Egyptians, the Babylonians appeared interested in solving practical problems to do with measuring and weighing. The Babylonian solutions to these problems are written like mathematical recipes. A scribe would simply follow and record a set of instructions to get a result. Here's an example of a kind of problem they'd solve.
Now I've got a bundle of cinnamon sticks here, but I'm not going to weigh them. Instead, I'm going to take 4 times their weight and add them to the scales. Now I'm going to add 20 jinn. Jinn was the ancient Babylonian measure of weight. I'm going to take half of everything here and add it again. So that's 2 bundles and 10 jinn. Now everything on this side is equal to 1 manna. 1 manna was 60 jinn. And here we have one of the first mathematical equations in history. Everything on this side is equal to 1 manna. But how much does the bundle of cinnamon sticks weigh? Without any algebraic language, they were able to manipulate the quantities to be able to prove that the cinnamon sticks weighed 5 gin. In my mind, it's this kind of problem which gives mathematics a bit of a bad name. You can blame those ancient Babylonians for all those tortuous problems you had at school. But the ancient Babylonian scribes excelled at this kind of problem.
Intriguingly, they weren't using powers of 10 like the Egyptians. They were using powers of 60.
The Babylonians invented their number system, like the Egyptians, by using their fingers. But instead of counting through the 10 fingers on their hand, Babylonians found a much more intriguing way to count body parts. They used the 12 knuckles on one hand and the 5 fingers on the other to be able to count 12 times 5, i.e. 60 different numbers. So for example, this number would have been 2 lots of 12, 24, and then 1, 2, 3, 4, 5 to make 29.
But the number 60 had another powerful property. It can be perfectly divided in a multitude of ways. Here are 60 beans. I can arrange them in 2 rows of 30, 3 rows of 20, 4 rows of 15, 5 rows of 12, or 6 rows of 10. The divisibility of 60 makes it a perfect base in which to do arithmetic. The base 60 system was so successful, we still use elements of it today. Every time we want to tell the time, we recognise units of 60, 60 seconds in a minute, 60 minutes in an hour. But the most important feature of the Babylonians' number system was that it recognised place value. Just as our decimal numbers count how many lots of tens, hundreds and thousands you're recording, the position of each Babylonian number records the power of 60 you're counting.
Instead of inventing new symbols for bigger and bigger numbers, they would write 111, so this number would be 3,661. The catalyst for this discovery was the Babylonians' desire to chart the course of the night sky.
The Babylonians' calendar was based on the cycles of the moon, and so they needed a way of recording astronomically large numbers. Month by month, year by year, these cycles were recorded. From about 800 BC, there were complete lists of lunar eclipses.
The Babylonian system of measurement was quite sophisticated at that time. They had a system of angular measurement, 360 degrees in a full circle. Each degree was divided into 60 minutes. A minute was further divided into 60 seconds. So they had a regular system for measurement, and it was in perfect harmony with their number system. So it was well suited not only for observation, but also for calculation.
But in order to calculate and cope with these large numbers, the Babylonians needed to invent a new symbol. And in so doing, they prepared the ground for one of the great breakthroughs in the history of mathematics: 0.
In the early days, the Babylonians, in order to mark an empty place in the middle of a number, would simply leave a blank space. So they needed a way of representing nothing in the middle of a number. So they used a sign as a sort of breathing mark or a punctuation mark, and it comes to mean 0 in the middle of a number.
This was the first time 0 in any form had appeared in the mathematical universe. But it'd be over 1,000 years before this little placeholder would become a number in its own right. Having established such a sophisticated system of numbers, they harnessed it to tame the arid and inhospitable land that ran through Mesopotamia. Babylonian engineers and surveyors found ingenious ways of accessing water and channeling it to the